This is TWiT.
This is probably my favorite talk title of this summer's DEF CON Black Hat 2021. This is a play on You're Doing It Wrong. This is You're Doing IoT RNG. So, obviously, Internet of Things random number generator. A pair of researchers from Bishop Fox Labs titled their talk, You're Doing It IoT RNG. They dug into the source of entropy being used by some of today's most popular IoT platforms, and actually, apparently by all of them. And to say that they found it wanting would be an understatement. To get their audience's attention, they began by noting, quote, "There's a crack in the foundation of Internet of Things security, one that affects," Leo, you're centered over your ball, "one that affects 35 billion devices worldwide."
Oh, my God. What?
35 billion with a B. I think that's all of them. Basically, they said every IoT device with a hardware random number generator contains a serious vulnerability whereby it fails to properly generate random numbers. And Leo, if this sounds like an echo of podcasts past, well, yes, because, of course, we talked about all this stuff a long time ago.
Historically, computers are terrible at random numbers. That's why most of the time they're called pseudo-random number generators, right?
Correct.
Yeah.
And as we know, pseudo-random number generators tend to be resource intensive. Anyway, they finish by saying this undermines security for any upstream use. Okay, so let's roll back a little bit. Many years ago on this podcast, when we were laying the foundation of cryptography and the requirements for securely encrypting both data at rest and data in flight, which is to say communications, we explained the importance of a high-quality source of entropy. As an example, we often talk about the very popular Diffie-Hellman key agreement system, where each side picks a number at random, turns it into a key by performing some crypto math on it, then sends it to the other side. Thus they exchange these keys. And the cool thing about this, which makes it so valuable for securing communications, is that each side is able to make their originally chosen random number themselves. They're able to take their originally chosen random number along with the key they receive from the other party, and combine those to arrive at a new key. And each side of this connection, or this nascent connection, will arrive at the same new key. But the most critical aspect of this is that anyone eavesdropping on that initial communication is able to observe and obtain the keys for themselves, which each side sent to the other. Yet even so, that eavesdropper is unable to recreate the key that both ends now share. So this allows the ends to then start using the key that they now share to establish truly private communications. They then use that as an encryption key, or they chose, one of them chooses a key at random and then uses the shared key to encrypt that to send it to the other end. There's all kinds of ways to skin that cat, given that you've got these fundamentals. Nothing, however, more fundamental than having entropy, being able to pick a random number. That's the first thing that each side did. They chose a random number. And it's crucial to the security of the entire process that each side's chosen random number cannot be known or guessed by anyone else. Another example, famously, was Dan Kaminsky's observation that DNS servers were emitting IDs in sequence rather than randomly, which allowed all of the anti-spoofing measures to just be short-circuited, to be collapsed. So the need for randomness is everywhere, and that number must be truly random. But it turns out that it's much easier to specify what we want from a random number or in a random number than it is for a little computer sitting inside a light switch or a webcam to actually generate such a number. So a random binary number we would define as any string of bits of some specified length where the probability of each bit being a 0 or a 1 is exactly 50-50, and each bit is chosen completely independently of any other of the random bits. Right. So, and what you're going to end up with is a big bunch of random bits where there's no association, no connection between them. So it's easy to ask for, but software won't do that, right? It won't. It's brutally deterministic. No matter how much you add, subtract, multiply, and divide, if you start from the same starting point, you're always going to arrive at the same ending point. So, in order to break this deterministic cycle, we need some external source of unpredictability. A little so-called system on a chip, right? An SoC probably has a radio for Wi-Fi. So if it was clever, it might hash the Wi-Fi packets it's able to sniff buzzing around in the air, whether they're meant for it or not. And if it was extra clever, it might even tune its radio to different channels, or maybe listen to the noise being generated by the cosmic background radiation, or what we commonly refer to as static. It might periodically sample the value of collect a bunch of that stuff, hash it all, and then dump the results into a growing pool of entropy. And then what we would have is a cryptographically secure pseudo-random number generator, a CSPRNG, that would be designed in software to take that pool of entropy and produce a series of really high-quality keys. Technically, each one is not random because at that point it's based on software, but it's pulling from a large enough pool of true randomness that it is cryptographically strong enough for our purposes. And after using it for some length of time, we decide that we've pulled as much entropy out of that pool as is safe to do. And hopefully in the meantime, our little hardware generator has been, sniffing more static from the ether and preparing another pool for us to switch to. And this is, classically how things are done in big operating systems. Linux does something exactly like this, pulling from a bunch of different sources of entropy, pouring it all in. And we talked about that. We did a podcast, in fact, once called Harvesting Entropy, where I talked about the system very much like this that I designed for Squirrel in the early days of that work.
What Cloudflare has in their lobby, which is a bunch of lava lamps. And
with a webcam.
With a webcam, apparently chaotic enough that you're getting some pretty good entropy. With the lava lamps.
So it turns out this is not what happened in our IoT devices.
Of course it's not. What a surprise.
For one thing, many of these systems on a chip are very resource constrained. They don't have enough extra RAM to, they're barely enough to hold the stuff they need, let alone create a sufficiently large pool of entropy. So the designers of the hardware said, okay, we can do this in hardware. And they built in their own source of entropy noise. One of the fundamental components in electronics is a diode. Probably everybody knows a diode uses the properties of semiconduction to only allow an electric current to flow through it in one direction. Well, okay, at least in theory. It strongly resists any current flow in the opposite direction. But there's a limit known as the diode's breakdown voltage, above which a diode will start to leak in its reverse direction. And it turns out that as individual electrons valiantly tunnel their way essentially upstream or against the diode's attempt to block them, they do emerge victorious on the other side. This breakdown current is quite noisy. It doesn't have any sort of perfect 50-50 property to it yet, but it is utterly unpredictable because it's just based on quantum physics, literally quantum physics tunneling of electrons. So it can serve as a starting point for the system on a chip's full built-in hardware random number generator, which needs to do a bunch of like whitening and purifying and balancing in order to bring us to like 50-50 probability bits, which is what we need. So it needs to do a lot of work still, but it doesn't need, it's able to do it all in hardware. And it gives us something that meets that simple definition that we began with.
Can I ask you, just parenthetically, does it then use that as the seed for the random number generator, or is it more sophisticated than that?
It's actually more sophisticated than that. It takes a bunch of that and it compares them with each other. Like if you've got a bunch of bits that are not 50-50, but if you XOR them with others that are also not 50-50, it ends up quickly falling out. So you're able to do some hardware tricks that are very simple and give you high quality randomness given the particular characteristics that this like the low level electron event thing produces.
That becomes the random number generator then.
Yes, exactly.
That's the number. Those are the random numbers coming out of it. I get it. Okay.
It turns out that we're back to a resource constraint problem almost immediately. And IoT hardware has taken a shortcut of using a pure hardware generator that unfortunately, Leo, and here's where it comes out, has a limited rate of entropy generation. The reason our Linux OS uses an entropy pool is that the scientists who designed this understood that we might be measuring network packet arrival time with high resolution. We might be pulling data out of the processor. There are all these performance counters, how many branches are taken and not taken, how many clock cycles have we had. So you can take all these different sources that are unpredictable, but none of them are super high rate. So this is the reason you accumulate them in this entropy pool, and then you used software to churn that in order to satisfy the operating system's maybe very hungry need. A server that is actively terminating thousands of connections per second, right? It's accepting incoming queries, individual TLS connections. It's hungry for entropy. It needs entropy for every single one of those TLS connections that it terminates. It has to have randomness. So we solve this problem on a mature OS with a hybrid. We take a low rate source of entropy and then we accumulate that in a pool and then use software. Systems on a chip don't do that. Writing about the need for IoT devices to have entropy sources, Dan and Alan, who are with Bishop Fox, the people who presented this DEF CON presentation, explain that, quote, as of 2021, most IoT systems on a chip have a dedicated hardware random number generator peripheral that's designed to solve this problem. That is, the need for entropy. They said, but unfortunately, it's not that simple. How you use the peripheral is critically important, and the current state of the art in IoT can only be aptly described as doing it wrong. Okay, so get a load of this. The researchers found example after example where the code that was calling the hardware's built-in random number generator API always assumed that the API call succeeded in providing them with with the valid random data they had requested, and the code never bothered to check for the error status returned from the API, stating that the request could not be met at this time.
Wow.
So if you think about it, the really tricky thing about this is that if you're asking for random data, anything that is returned is valid, right? I mean, as unlikely as it might be, getting all zeros back from a request for a completely random number would not be itself an error, since while it would be incredibly unlikely, it's possible. So if you don't deliberately check the success or failure status of a request for random data, you'll still get data, but it might not be at all random. A GitHub search for this mistake made in IoT code based upon the very popular MediaTek 7697 system on a chip hardware abstraction layer, their HAL. Look, the search for the mistake found 3,218 separate hits in GitHub. And a similar GitHub search for mistaken use of the hugely popular free RTOS IoT operating system turned up looking for the mistake, right? Mistaken use of this in free RTOS turned up 36,696 instances of improper use. As the authors wrote in their write-up where they show the C code snippets, they said, quote, "Notice that the return code is pervasively not checked. Though this isn't unique to these two examples, this is just how the IoT industry does it. You'll find this behavior," they wrote, "across basically every SDK and IoT OS." So as not to put any words in their mouth, I'm going to quote from their write-up under what's the worst that could happen. They said, okay, so devices aren't checking the error code of the RNG HAL function, the random number generator hardware abstraction layer function. But how bad is it really? It depends on the specific device, but potentially bad, very bad. They said, let's take a look. The HAL function to the RNG peripheral can fail for a variety of reasons, but by far the most common and exploitable is that the device has run out of entropy. Hardware RNG peripherals pull entropy out of the universe through a variety of means, they said, such as analog sensors or EMF readings, but don't have it in infinite supply. They're only capable of producing so many random bits per second. If you try calling the RNG HAL function when it doesn't have any random numbers to give you, it will fail and return an error code. Thus, if the device tries to get too many random numbers too quickly, the calls will begin to fail. But that's the thing about random numbers. It's not enough to just have one. When a device needs to generate a 2048-bit private key, as a conservative example, it will call the RNG HAL function over and over in a loop. This starts to seriously tax the hardware's ability to keep up, and in practice, they often can't. The first few calls may succeed, but they will typically start to cause errors quickly. So, what does the HAL function give you for a random number when it fails? Depending on the hardware, one of the following: partial entropy, the number 0, or some uninitialized memory, which is to say something, but it doesn't ever change because it's just memory somewhere. So, as a consequence of this, the feeling of security that we all have is illusory with our IoT devices. Oh, yes, we have TLS. Yay. But if the TLS handshake is based upon all zeros or static unchanging keys, then TLS is just adding a bunch of overhead on the connection and not providing any true privacy. As I've noted before, the entire world has rushed headlong into IoT without any standards, nor anything like an underwriter's laboratories for device security. Outside, the box says, uses the most advanced military-grade encryption, but fails to mention that it also uses null crypto keys. Whoops.
They're not technically wrong.
Think that might matter? Oh, Lord. Yes. So anyway, good to know. It's a function of the design. These guys discovered that any device where it's with the application running on the IoT OS is asking for lots of entropy, and who knows? It depends upon what the app is doing. The device might run out of it and just say, no, you can't have it. But that refusal doesn't ever get checked, even at the OS level. It's not that the app isn't. When they talk about the HAL, the hardware abstraction layer, they're talking about a sort of a generic IoT OS, which has been ported to a bunch of different underlying hardware, and it doesn't check. So the API just says, yeah, here's your entropy, even if it's zeros.